All right, this is assignment number 25. I did include problem 53 on my answer key, but I see that in my instructions for the homework assignment, we're told to skip 53. Also, it says to do for only part A. I'm not actually sure how to do part B. I'd have to look into that. So part A for number 4 says find a geometric power series for the function centered at 0. By techniques shown in examples 1 and 2. So that's like we just did in the notes where we can build a geometric series. So how do we build a geometric series? Remember, the first thing is that you want to make sure this says minus r, which it does, minus x. If this were a plus, I would write it as minus negative x. The next thing is that this number should be a 1. So if I multiply by 1/5 on the top and the bottom, that's legal math because you're really just multiplying this fraction by 1. You're not changing the value of the fraction. But that makes this now 2/5 over 1 minus x over 5. And this is the sum of a geometric series. So what is the geometric series? That's the whole that's the whole point of the question. Remember, the top number is the first term in the series, so it's a. In this case, it'll be a sub 0. And the r is what you're subtracting, 1 minus r. So r is x over 5. Again, if this were plus, I would have r as negative x over 5. And so I just write that down, a times r to the n. I started this at 0 because if this is the first term you're supposed to get, you just put in 0 here and you'd be left with 2/5 times 1. And that's the sum of my series. Now, this didn't ask for an interval of convergence, but just to follow up with that, the interval of convergence would be anything between -5 and 5 by the geometric series test. I might have posted more details on that, but geometric series test says that absolute value of r needs to stay less than 1. That just keeps this expression between -1 and 1, and then I multiplied by 5. And you don't need to check endpoints for a geometric series because the rule is that r has to be less than 1. There are no other n's in a denominator out here affecting whether this series is decreasing, if it's alternating or something. All right, for the next part, it says find a power series for the function centered at c, determine the interval of convergence. So our function is 1 over 3 minus x. Our center is supposed to be 1. So remember, that means that when you're building this, you're going to have x minus 1 of some sort to the n. So that means that r needs to be x minus 1. All right, so how do I put an x minus 1 in here? So the first thing I'm going to do is just go ahead and put it in where I want it. So I want this to be minus the quantity x minus 1. And I can't just do that because that changes the value of the fraction, but I can do that if I turn around and undo what I just did. So what did I just add to the problem? This is really negative x plus 1. So if I've really just added 1 to the denominator, I can turn around and undo that by subtracting 1 in the denominator also, because this would simplify back to 3 minus x, right? Okay, so now the function is 1 over 3 minus 1. Let's simplify that. That's 2 minus the quantity x minus 1. All right, what else are we supposed to do? We're supposed to get this to be 1 minus r so that it's in the true form of the sum of a geometric series. So now go ahead and divide by 2, top and bottom, or multiply by 1/2. So that now makes this 1/2 over 1 minus, let's just merge that together, x minus 1 over 2. So this is still f of x. This complex fraction is equivalent to this original fraction. If I were to graph these two versions of f of x, they would be the exact same graph. But now it's in the form where I can see, okay, the first term of my power series is 1/2, and the r, the common ratio that I should be getting if I divide consecutive terms, is x minus 1 over 2. So now we can write a power series for that. It would go from n equals 0 to infinity of 1/2 times the quantity x minus 1 over 2 to the n. All right, determine the interval of convergence. So again, these are geometric series, so I don't have to use ratio test and check endpoints. I can just say this series converges by the geometric series test if the absolute value of x minus 1 over 2, r, stays less than 1. That means that that fraction just needs to stay between -1 and 1. Start solving. -2 is less than x minus 1, which is less than 2. R is 2, by the way, the radius of convergence. It didn't ask for that, but I think it's a good habit to be able to pick that out. Add 1 to both sides, and you get anything between -1 and +3 for x is my interval of convergence. And again, I don't need to test the endpoints because remember, there are no extra ends outside of the R that are acting on this that could give it the possibility of converging. It's not going to turn into an alternating series or some sort of P series or something if we plug these endpoints in. This one has a center of 0, so I don't need to do any extra magic with like putting in a -1 + 1. Okay, so that's nice. I am going to spin this around a bit. So this is going to be 2 over, I want the constant term first. And even though it's plus 2x, we need this to get into the form of 1 minus r. So let's make it minus -2x. Still equivalent, right? We haven't changed the value of f of x. Now I need this to be a 1 instead of a 3, so I'm going to multiply by 1/3 over 1/3. So now it's 2/3 on top over 1 minus -2x. Oh, I almost forgot to divide that by 3. Over 1 minus -2x over 3. So this is f of x. Again, I should be able to graph the original f of x and my new f of x in Desmos, for example, and see that they're the exact same graph. I've just set this up to look like a geometric sum. So a is 2/3. R is -2x over 3. So the sum of the series goes from n equals 0 to infinity. It's 2/3 over -2x over 3 to the n. This converges by geometric series test if the absolute value of -2x over 3 stays less than 1. Let's get the negative out of there because this is an absolute value. So that just means 2x over 3 should stay between -1 and +1. Multiply the 3 out to both sides. R is 3, by the way. And then divide by 2. So as long as x stays between -3 over 2 and +3 over 2, we have a power series that will converge. We don't know, we do know, we do know what it converges to. If they asked me to follow up, like, okay, so, well, I guess I wouldn't need that, but does the series have a sum at x equals 1, then I would say yes, because this converges. And what is the sum of the series at 1? It's just f of 1. I would just plug in 1 and say, the sum of the series is 2 over 5 at x equals 1. All right, take a look at the next part. So this is giving us a power series to use. They're saying, all right, here's a geometric series, 1 over 1 plus x, which is -1 to the n times x to the n, or it could be -x in parentheses to the n. Use that to determine a power series centered at 0 for the function they give us. Identify the interval of convergence. So notice for this first one, they're showing us, okay, h of x is -2 over x squared minus 1. They've done the partial fraction decomposition for us. And we can say, all right, they gave me a power series for 1 over 1 plus x. And I know a power series for this geometric one. This is one I have memorized. Or you can say a is 1 and r is x for that. So let's go ahead and write those out. I'm going to write them separately to start. So the first one was given to me. It's n equals 0 to infinity of -1 to the n times x to the n. We're adding to that the geometric series that we have memorized, or I can use, a is 1 and r is positive x. So that one's just x to the n. And these two summations have the same bounds. They're going from 0 to infinity. So we can merge these together, just like we do for integrals that have the same limits of integration. We're allowed to do that, like this. And then let's do a little bit of factoring. I have two terms that both have an x to the n in it. So let's go ahead and factor that out. What would that leave me with? It would leave me with -1 to the n plus 1. All right, now what do I think about this? Well, depending on what n is, I'm either going to get -1 plus 1, which is 0, or 1 plus 1, which is 2. So you're trying to come up with, what are we trying to do? Come up with a power series that's more simplified than this, I would say. So, like, yeah, I guess I could leave it like this, but if we're in multiple choice answers, they're not going to have this as your answer. So, okay, so what is it? Start expanding out terms. Just give yourself a few terms until you see maybe a pattern. So, I'm going to write out, I don't know, maybe let's go out to n equals 3, see what happens. So, if I plug in 0, I get x to the 0. If I plug in 0 here, -1 to the 0, you do need to know that is +1. Just like because 0 is even, so -1 squared is 1. Anything to the 0 is +1. All right, so anyway, so if I plug in 0, I get x to the 0, which is 1, times 1 plus 1, which is 2. If I plug in 1, I'm going to get x to the first times 0. If I plug in 2, I'm going to get x squared. And plug in 2, you get 1 plus 1, so plus 2x squared. Plug in 3, you're going to get 0 again, 0x to the third. Let me just show one more. N equals 4, so okay, that's going to be plus 2x to the fourth. So you can see what's happening here, right? All of the even terms survive, and they have a 2 in front. All of the odd terms come out to 0. So let's clean it up a little bit. It's going to be 2 plus 2x squared plus 2x to the fourth. I can guess the next term, plus 2x to the sixth. Keep going. Let's write a simplified series for that. So I don't need an equal sign there. Every term has a 2 in front. And these are all just even exponents. If n is 1, that's 1 times 2. If n is 2, that's 2 times 2. N is 3, 3 times 2. So you can rewrite the n's if you want to help you see the pattern. So yeah, that's going to be x to the 2n. 2 times x to the 2n. And that's not the same as 2x in parentheses to the 2n, because the 2 is constant. It's not going up by an exponent. All right, so that's going to be my power series. What's the other reason I would need to simplify that? Because remember, we're also supposed to find an interval of convergence. So it's hard to do an interval of convergence on this back here, but it's much easier to do it here. I can say this is geometric again. So this series converges by the geometric series test. Now technically this is x squared to the n. So if the absolute value of x squared is less than 1, you don't need an absolute value around x squared. If you square root here, remember this is actually absolute value of x, so don't put a plus or minus here. The plus or minus comes out when you split that apart. As long as x stays between -1 and 1, you have something that converges. All right, what about 21? They're telling us ln of x plus 1 is equal to the integral of 1 over x plus 1. Remember, they're giving us the series for 1 over 1 plus x. So let's go ahead and say we're going to integrate the power series that they gave me. They gave me -1 to the n times x to the n. We're supposed to integrate this thing. So we know how to do that. Remember, we hold off on assigning an n yet. The -1 to the n would still be there. This would become x to the n plus 1, and you divide by the new exponent. All right, and then what would this be? So let's see. So the 1 over x plus 1 terms, if you put in, they start at 0. N is never going to start at -1. So if I start at 0, that's okay as long as I don't get an x to a negative. So 0 is fine because you'll start off getting x to the first over 1. So that's correct. And I'm supposed to find the interval of convergence for this. So I can't use geometric series test on this one because it's not geometric. So I'm going to use ratio test. The limit as n approaches infinity of the absolute value of x to the n plus 2 over n plus 2 times n plus 1 over x to the n plus 1. The x's will cancel just to x to the first. The ends are going to go toward 1 as you approach infinity. So this is like having 1 times x in here. So this comes out to absolute value x. And this converges, the series converges by ratio test if absolute value of x stays less than 1. That means that x should just stay between positive and negative 1. And I do need to check the endpoints on this because I used ratio test instead of geometric. So let's check if x equals negative 1. What would the series be? You're plugging back into this one. Remember, this is our power series for ln of x plus 1. So plugging back into here, I would have the negative 1 to the n. And now there's another negative 1. It's to the n plus 1 over n plus 1. You need to simplify this more on an AP free response. And just for your own self, like what are you looking at here? So add these exponents. This is 2n plus 1. 2n plus 1 is always odd. So if you're always raising negative 1 to an odd power, you might as well just write that you always have a negative 1 in the top. This is not an alternating series. It's a general harmonic series. So this would diverge. How do I show that a general harmonic diverges? You can either say by integral test, or it could be limit comparison test to the harmonic series. Okay, and then what about if I have x equals 1? So you would have the negative 1 to the n. And then 1 to the n plus 1 is just 1, so that doesn't need to really be in there, over n plus 1. Now this is an alternating series, and its terms are approaching 0, so this would converge by alternating series test. So the final interval of convergence, here's my power series. The interval of convergence is negative 1 is less than x, which is less than or equal to positive 1. Or you can use interval notation, parentheses on negative 1, square bracket to include positive 1. All right, let's take a look at 22. 22 is saying ln of 1 minus x squared is the integral of this term minus the integral of this term. Now, we just did all of this work here on this one. So remember, you already have a power series for what that integral is. So you could either, I guess I did it, let's see, which way did I do it on my key? I kept them separate. Like, let's say I haven't already done this. I think that's probably the best way to approach this. So let's pretend I have not already integrated the series for integral of 1 over 1 plus x, just to see what would you do if you were starting fresh. So I would say, all right, we've got the integral of the power series they gave me. Oh, doesn't need to be up here. I was setting up a fraction. Make that nicer looking. So that's this thing. Minus the integral of, this is a power series I know, or I can quickly build. It's geometric. It's just x to the n. There should be dx's here for my integrals. Go ahead and integrate then. So this power series will be negative 1 to the n times x to the n plus 1 over n plus 1. And this one will be from 0 to infinity, x to the n plus 1 over n plus 1. All right, and we're going to do the same thing that we did before. So I think we can, excuse me, I think that we can factor or get this together first. I feel like I'm going in a slightly different order than I did on my key, so see if this makes any more sense if you're watching this video. Looking at the key might not have done it for you. So we have almost the same two terms being subtracted within this summation. So that means that we can factor out what they have in common. We can factor out an x to the n plus 1 over n plus 1. And what would that leave me with? The first term would have a negative 1 to the n minus a 1. So we saw this before. This is going to either give me 0 or I guess negative 2 in this case, instead of positive 2 like we had before. So just expand out a few terms for yourself. I like to remind myself what n I'm plugging in. All right, so if I plug in 0, let's start with the 1's first. Negative 1 to the 0 is 1. 1 minus 1 is 0. So the first term will be 0. x to the first over 1. The next term, when I plug in 1, negative 1 to the first is negative 1, so I'm going to get minus 2 times x to the second over 2. And then I'm going to get plus 0, right? 0, x to the third over 3. Then I'm going to get minus 2. When I plug in 3, I get x to the fourth over 4. I just want to do a couple more terms just to make sure the pattern's clear, because I see these are simplifying a bit. Plus 0, x to the fifth over 5, minus 2, x to the sixth over 6. This simplifies, right? That's 1 half, that's 1/3. So what is my simplified series here? I start off by getting, look at the non-zero. Actually, let's rewrite this so we have just the non-zero terms out of the way. So it starts with negative x squared minus x to the fourth over 2 minus x to the sixth over 3. So this is always negative. X to the, maybe we don't start at 0 here. X to the 2n, as long as n is 1, 2, 3, over n. So as long as we start at 1. Did I have that? No, I did have a slightly different thing on my answer key that I posted. So see if this helps at all. All right, so then for this series, I want to come up with, this is my, sorry, let me rewrite this so it's not so close together. Let's get this out here a little bit. Lost a couple pieces there. Okay, so this is what I'm saying my power series is for ln of 1 minus x squared. And what would my interval of convergence be? So my interval of convergence should be the limit as n approaches infinity of the absolute value, so get rid of the negative, x to the 2n plus 2, because you're putting in n plus 1 there, over n plus 1, times n over x to the 2n. This should leave you with the absolute value of just x squared, right? Because the n's approach 1, and subtract those exponents, you get x squared. So I'm back to this interval of convergence where we say, okay, absolute value, unnecessary. Square root both sides. Okay, that gives you absolute value x is less than 1, which means x can fall between negative 1 and 1. I do need to check the endpoints. So let's say if x is negative 1, what does the series look like? So back here, there's a negative built in, and then it's negative 1. So let's call that, you know what? Let's write that negative as a negative 1. Multiply by negative 1, and then you have negative 1 to the 2n over n. Now, negative 1 to the 2n will always be negative 1 to an even, so that'll just be 1. So you're really just left with negative 1 over n. That diverges because it's the harmonic series. It's the harmonic series times negative 1. What if x equals 1? That makes this n equals 0 to infinity. Negative 1 is built in. Then you get 1 to the 2n over n. 1 to the 2n is also just 1. So this also diverges. It's a harmonic series again. So we do not include either endpoint. So here's my power series. And here's my interval of convergence. I did have a slightly different power series because in my answer key that I did before, because before I integrated, instead of integrating first and then combining, I combined first and then I integrated. But if you generate the terms of what I wrote on the PDF, it would give you the same thing. I had it starting at 0, which means I needed an x to the 2n plus 2. And it needed to be over, it was still over n plus 1 instead of n. But yeah, that generated the correct terms. Okay, let's see. Do we have time for these last two? I don't know. Let's see how far we can get here. All right, so we need f of x equals arctan x. We're trying to approximate whatever the value they give you to less than or equal to 0.001. So I can use I'm going to use a calculator for this one. I'm going to let it open while I work on this. So the function is arctan x. Let's start there. We don't have this one memorized. So we need to come up with, like, what is f prime x? It's the derivative of arctan is 1 over 1 plus x squared. And how did I know that? Because remember, when we integrate this, that answer is arctan. So just go backwards for the derivative. Now, I can write I don't want to come up with a series of derivatives for this to find a pattern. I want to have a power series that I can work with for f of x to start. So it says use the series for f of x. So let's come up with that series. Now this is geometric. This is 1 over 1 minus x, 1 minus negative x squared. All right, so that tells me a is 1 in this geometric series and r is negative x squared. So I do have a power series for f prime. It's the sum from 0 to infinity of 1 times negative x squared to the n. And you can just make that like that's negative 1 to the n, x to the 2n if you want to. I think I am going to simplify that. Negative 1 to the n, x to the 2n. All right, so then how does that help me? Remember, we're trying to get a series for f of x. So now f of x is equal to the integral of f prime x dx. And we just came up with a series for f prime. So we should be integrating the sum from 0 to infinity of negative 1 to the n times x to the 2n. All right, dx. So let's integrate that. That's going to make this negative 1 to the n still there. X to the 2n, you add 1 to your exponent and divide by the new exponent. All right, so this is our f of x power series. And we want to keep this power series less than or equal to 1. So let's think about this a little bit. It doesn't say whether I have to use Lagrange or if I can use alternating. So this series is alternating. So I can go ahead and use the alternating series test. I can say if I'm trying to approximate some remainder by plugging in 1/4, and I want to keep that less than or equal to 0.001, it should just be less than or equal to the first neglected term at 1/4. And then we're trying to keep that less than or equal to 0.001. So what would that be? Well, our function is this. So let's go ahead and plug 1/4 into that. So that would be, and we've got to plug in n plus 1 into that. Sorry. So instead of x to the 2n plus 1, it's going to be 1/4. And add in n plus 1 here. So 2n plus 2 plus 1 is 2n plus 3. Put n plus 1 in down here. You also get 2n plus 3. Less than or equal to 0.001. Now, I could probably go through this non-calc if I needed to. I could say, all right, I've got a 4 to the 2n plus 3 down here. I'm multiplying by 2n plus 3, and I'm trying to compare that to 1 over 1,000. So you can do that if you'd like to, or I'm just going to use my calculator just to speed things up because I'm almost out of time here. So I can alpha fraction it if I want to. Make that 1 over 4 to the 2x plus 3 times 2x plus 3. If you don't have the fraction capability in your calculator, you would just need parentheses around that whole thing. And then let's make sure the window is starting at like 0. So second window, 0. Second graph for table. And, oh, hey, it only takes n equals 1, which is crazy. So I get through this with n equals 1. That's why I say it probably could have been a non-calc problem. What do I have to do with this? I've identified n equals 1. Use the series to approximate the value. So they want me to approximate the arctangent of 1/4. So arctan of 1/4 should just be me taking this series out to one term. So I've got to use n equals 0 and n equals 1 to approximate. So plug 0 into this. Negative 1 to the 0 is 1. X to the first, so 1/4 to the first over 1. and then put in 1, you get minus 1/4 to the, put in 1 here to the third, over, put in 1 in the bottom, 3. Now we are talking about being an absolute value. Or no, we're not. Sorry, this is not an error. So I'm going to calculate what this is. Now this is just 1/4 to the third, so 1/64 times 1/3. So I'm getting that arctangent is approximately this value. Let's check that. Is arctangent of 1/4 close to that? No, what happened? Let's see. Oh, whoops, I forgot. There's a 1/4 in front of here too. So this answer. But let's insert in front of that a 1/4 minus. Let's see. Better. Okay, so here's my approximation. Good thing I checked, huh? And here's the value for arctan. I forgot I had this whole term in front of here. So we're getting that this is approximately, let me write this down, 0.244. See how they match to 3 decimal places? That's all we needed. 7916 repeating. All right, I need to stop there because class is about to start. I will do a video to finish just the last problem here.